Thanks a lot, Professor. As we already mentioned in the introduction, before recording started, the initial version of the seminar was already given at the Center of Theoretical Physics a few months ago. So you may have some overlap with what happened already, but we have some maybe deeper understanding now of our results. So this project was done in the collaboration between, of course, our faculty, Institute of Photonic Sciences, where I'm doing another part of my PhD, and University of Hamburg, which was an experimental team whose results we were analyzing. And the background, this pictures were actually the pictures which we were given to the machine, and of course I will explain every element of this procedure. And the results were published last year in Machine Learning Science and Technology. And as I mentioned, this is the team. So both ICFO and Hamburg, represented by and led by Alexander Dauphin and Christoph Weitenberg. So what was our goal? The ultimate goal of machine learning for phase classification, I would say, is to detect phases straight from experimental data. The idea is to really remove any bias that could be introduced by physicists who may expect some phases. And with this purely automated way, we may hope for discovering new physics, which would maybe elude us up till now. And obviously, the final goal would be then apart from detecting phases, we also understand order parameters, and this would be the holy grail of this subfield. Of course, we're still far away from that, but we are getting closer, and this paper is one of the proofs for that. So our goal was to analyze time-of-flight images generated by the system. I will explain what the system is and how to get such data. And we feed it to the machine in a fully unsupervised way, and you want to discover the phase diagram. Here we, of course, are cheating a little bit because we have some theoretical predictions that we start with, and this is, again, it's still more proof of a concept than true scientific discovery or knowledge discovery, but we're still not there as a community, I would say. But even though it's just a proof of concept, it's already pretty challenging. And why is it? So first of all, experimental data is noisy. They have many additional features which are not effect of, let's say, physics of underlying model. It's more about experimental realizations. And they may change the image itself, and it can fool the machine into thinking it's something really important and something to focus on. And finally, there's the third argument that people noticed within last 5 years that topological models are pretty challenging for machine learning models to really see the phases there. And why is that? We don't have a definite answer why it's challenging, but we suspect it's because of the global nature of order parameters. And we know from some other research that machine learning models have tendency to focus on local information instead of looking at the same time at everything, let's say. So I would say this is our hint why it's challenging for machine learning models. Okay, so this is the goal. I hope now you know why it's also a kind of ambitious goal. And now I will explain how we got final results and what kind of cheating we did on the way. So I will start with describing the model and the system and experimental realization. And this is the moment when you can destroy me with questions, because of course I'm not an expert on experiments, on experimental realization, but I will do my best. Then I will describe the machine learning methods we used. And this is pretty technical part because we needed to use a series of techniques, but I hope I will be able to explain it as intuitively as possible, without getting to like maybe too much into detail. And then finally, we will show you the pipeline that we followed. That was that we started with the most optimistic approach, which was let's just cluster raw data. Then we encountered a problem coming from experimental realization, which was the micromotion. And I will explain what it is and why it was a challenge to overcome. So it was a feature we had to remove, and we did it with machine learning approach. Then we again used unsupervised approaches for this data without micromotion. And then finally, we overcome the final problems coming from the and detected all topological phases with influence functions. But this may sound like a complex story, but it has many elements. It's not difficult. That's okay. So let's start with the beginning. So what are these time of flight images? What we want to really analyze. So underneath model, which is a topological model, is two-dimensional Haldane model, and experimentally, it is realized by creating a honeycomb lattice, which is created by these three beams. And by controlling the polarization of these three beams, it's possible to create an energy offset between the neighboring sites. So you have this AB, AB, AB configuration. And this means that the inversion symmetry is broken. And it's one of two symmetries that it's needed to see the topological phase. The second symmetry that you need to break to see the topological phase and to really realize the diagram is to create non-trivial tunneling couplings between the neighboring sites. And here it's done by shaking the lattice. So this is why it's called a Floquet realization, because you introduce this shaking to your system. So when you see shaking amplitude, shaking frequency, it's exactly this kind of symmetry that you're breaking with it. And why I'm showing you these details. This is the thing that I'd like to discuss for a second. So when you shake your frequency, when you shake your system with some frequency, you can keep shaking your system for some time. And how long you shake your system isn't really gonna impact your physics in terms of topological phase, but it will introduce a different micromotion phase into your time of flight images. So you can imagine it as the moment when you stop shaking, this kind of momentum will be introduced to your system, and it will impact how rotated is your time of flight image. This is the intuitive picture. So there is some kind of rotation introduced to your time of flight images, which is connected to micromotion phase, which is being introduced by how long are you shaking your system. So, and it's not really, so it's a feature of experimental realization. It's not a feature of Haldane model. So maybe you already see what I'm hinting at. This will be a feature which will be really confusing for a machine learning model, and will actually prevent it from seeing topological phases, because it will think that micromotion phase is the most important. And of course, I will comment on that. Oh yeah, sorry. I just see that I have separate slide for micromotion phase, but exactly as I told you. So, for example, these are 7 time of flight images done for the same shaking frequency as shaking phase, which are 2 parameters determining the phase diagram of the Haldane model. But they have different micromotion phases coming from the shaking, and as you see, you have a little bit different rotation. Like it can be viewed a little bit as a rotation of the picture. So this would be the intuition. Okay, so this is the data that we're gonna play with, and we hope that they will encode. They will have enough information for us to decode this Haldane phase diagram with two trivial topological phases with chain number 0 and two non-trivial phases. Okay, so this was the physics part, and now about machine learning methods that we used. So I will start with a very brief, I will start with the definition just so we are on the same page, but I won't go into much of the details. But machine learning is a set of algorithms, of tools, whose performance improves with data. So it mimics our human learning from experience. However, the definition I like even more is this one. So these are approaches which solve problems without being told how exactly solve this problem. So in a sense, you can think about two approaches to programming. One is more knowledge-based. So you give to your program as much information as possible. You write a series of ifs, and conditions that needs to be met. It needs to be met to classify something into dog or cat. And what machine learning is all about, instead, you just give the data and you tell to the machine, figure it out yourself. So you find the features which are discriminative. You solve the problem yourself. I just want to get this outcome. So it's really data-based approach, and this is the source of all knowledge for the model. And how this data looks like and what kind of access your model has to data is determined by type of learning that you choose. So there are two most used in physics approaches so far, which is supervised and unsupervised learning. Supervised learning means that you give the data along with labels. So for example, here in our problem of topological phases, it would amount to giving time of flight images with a label being this time of flight image belongs and describes a system in this phase, and this time of flight image describes the system in this phase. So we give some solutions of the problem, and from these solutions, the model tries to learn the underlying, let's say, underlying rules, which it can then apply to unseen points. And in the contrary, there is unsupervised approach where you give just data without any labels, and this is what we are gonna do. And the idea is here that we really get rid of the human factor, and we have fully automated way of processing data. And then there's also a third type of learning, which I'm not gonna touch upon today, but it's called reinforcement learning. It's when instead of set of data, you create an environment with which your algorithm can interact, and it's, I would say, the most similar to how human experience is built. And it's also really interesting, and it's used for optimizing quantum experiments, this kind of stuff. But for today, we'll focus on these two approaches. So the largest focus I will put on unsupervised scenario, but I will also show you that in some moments we are using supervised one. Okay, so let's start with the simplest possible unsupervised approach, which may be even surprise to you that it's included in machine learning field, because it's simple clustering algorithm. And let's start with k-means clustering. So it's a very simple iterative algorithm where you start with unlabeled data. Here, it's two-dimensional just for us easier to make it easier for us to analyze it visually. You start with randomly set centers of clusters. And to this centers of cluster, you assign the closest points. Then out of the set of the closest points, you calculate, you shift the center to the center of mass of this cluster, and then you again assign the closest points, and you do it until you stop shifting your center of mass, and the set of points which is being assigned to this cluster stop changing. So you finish in this kind of labeled cluster image. And this is the first approach that we used. But for now, I will focus on methods, and then I will show you what we got from these approaches. The other approach, which is much more machine learning like, and so what I'm saying, you won't be surprised by someone saying that this is machine learning anymore. This architecture, this is a special type of neural network. It's called autoencoder. So what is autoencoder about? So this kind of connections, I will just, for someone who's not really sure what neural network is, I will just make a short introduction here. So this example, so this point with all connections before is called a neuron. What it does, it takes your input data, so all elements, for example, pixels of our time of flight images, it multiplies by some weight. These weights are parameters of your model that you need to vary during the training. And then you sum it up, all these products, you sum it up, and you get one number which gets transferred here. You usually apply some activation function, which is some non-linearity, and this is it. And and then this kind of architecture is done by connecting many neurons. And the crucial thing about this architecture, about an autoencoder architecture, is that inside it's not regular. You have a very narrow bottleneck. So you force your architecture to have a small number of neurons inside. And the whole idea of this architecture is that that it's supposed to reproduce your input data at the output. It would be pretty trivial if not for this bottleneck inside, because it really forces your model to compress whole data in some maximally meaningful way to then be able to decode everything at the output. So there are these two parts, encoder, decoder, and how your image looks like in this bottleneck. You can plot it really, what are the values of these two neurons. This is called latent space. And analysis in the latent space, which is compressed, let's say, which is a space of compressed features of your image, can make clustering much easier because it's more meaningful than clustering in a whole high dimensional space. So this is the idea of the autoencoder, which we're gonna use in our unsupervised approach. And then the final model that is needed to get everything that we did, it's still autoencoder, but now it's autoencoder with additional element. This additional element is called question neuron. Why it's useful? So underneath, it's exactly the same autoencoder that we had before. So the idea is to first encode your input data in this bottleneck, and then to decode it in such a way that your output and input is identical. But this time, if you add additional neuron, which is added to decoder, you can give some additional information to your model. And for now, it may not be obvious why it's useful, but when I show you our application, I think it will be much more understandable. But let's stop at this so we don't spend too much time on methods. So there is autoencoder, which I hope is understandable, and then you can add a question neuron. So let's stop at this message. And I will briefly go, because this is, of course, I'm cheating here at a little bit because this is not exactly the autoencoder we used, but I didn't want to go too much details. But for people who are familiar with machine learning, in fact, we are using variational autoencoder. The difference is that here, that at the bottleneck, instead of pure, let's say, numbers, we have probability distributions that we parameterize, and parameters of this distribution are the parameters of the model that we train instead of just weights. But this is just for more familiar for people more familiar in machine learning. Okay, so now we have set of methods, and how can we really apply it to our phase diagram? So, for example, there was a really nice paper which showed how you can use autoencoders to discover a whole phase diagram of some system in a fully unsupervised way. This was our inspiration to apply it to our system as well. And how you can do that? Imagine. So I told you this autoencoder is about reproducing the image that you put inside. Imagine you train your autoencoder on a part of your phase diagram, on a part that you know it's one phase. So it's, you know, it's uniform in the sense of the order parameter. Imagine you train your autoencoder there and you get good results. The autoencoder is able to reproduce this image at the output perfectly. And now imagine this was your training. This was a training phase. Now we stop training. We have trained autoencoder. Now imagine that you ask the same autoencoder to reproduce other states from your phase diagram, other parts of your phase diagram. And it turns out that as the further you go from this training region, the more confused autoencoder is. So the error of the autoencoder at reproducing these images, which are pretty different from this part of the phase diagram, increases. And by scanning the whole phase diagram, by how your autoencoder is wrong, you can see how many different phases you have, basically. So for example, here is the highest error, which means that this phase is much more different than this phase where you started your training. But you see that you can see much more interesting phases and phase borders only from this analysis of autoencoders. So this is the idea behind the anomaly detection scheme with autoencoders. And we're gonna use that. So this is, I hope, understandable. And now it's really final method that we use. But I told you this paper is a little bit technical in a sense. It's a series of different approaches. One wasn't working, so we were looking for something else. And but I believe that this will be kind of final approach for in the end. Machine learning for physics will be a series of tools which you need to know when to use one above another. Okay, but final tool, which is kind of my tool, my favorite tool, is influence functions. And I wrote it. I think I already explained to most of you what are these, but to some of you who still are not familiar, I'm happy to say it, to explain it. So what are influence functions? Basically, it's an interpretation tool. So they allow you to analyze your machine and check what it learned and how. They are approximation of something called leave one out training. It's a procedure which consists in training your model on your whole data set and training points, and making a prediction on single test point. So you have this. So this is a normal thing at machine learning. And now imagine you remove one training point from your training set. So you remove that. And now you train your model on n-1 training points. And you arrive to some model with a little bit different parameters. So the minimum of your training loss function switched a little bit, it shifted a little bit. And with this a little bit different model, you now make a prediction on your test point. And this prediction, there are three ways it can go. This prediction now may got worse. After removal of this training point, the prediction may got worse, so test point went higher. It means that the removed training point was a helpful example. The opposite can happen if you remove this one training point and retrain your model. It may happen that your prediction got better now. This means that you removed a harmful training example for this prediction. And of course, also there may have not been any change to the prediction, which would mean that the point which you removed was not influential. And with this procedure, you can really see what training points are harmful, what are helpful, and get some more insight into what machines think is influential in the problem. And you could do such a live-on-out training. This was actually a method from 70s used for linear regression. But problem is that it's very expensive for nowadays, for modern problems, because your training sets are huge and you would need to retrain it many times, and you don't do that. So instead, you are making these approximations, which are influence functions. And I decided that maybe I will try to show you an equation for that, because I think it's pretty intuitive, especially the geometric interpretation of influence functions. But what it does, this is the formula that we need to tackle. So what we need to calculate, so in the first step, we need to approximate how much your model changes after removal of a single training point. By how much your model is changing, we mean how parameters of the model change. So where is the new minimum of your training loss function after removal of the single training point? And you can approximate it by analyzing the curvature around your minimum and calculating basically a Newton step towards new minimum by calculating this kind of product. So the inverse of the Hessian calculated at the minimum multiplied by the gradient of the training loss function for the single removed point. So this gives us approximated change in parameters due to removal of the single training point. And now the last thing left to do is to calculate the product with the gradient of the test loss. So basically it answers the question how the prediction on a test point would have changed if the model parameters would be modified due to removal of a training point. So it's pretty intuitive after all. Also, and for more geometrically inclined people, there is also other intuition which is pretty powerful. You can just look at it as a scalar product of two gradients: gradient of a test point, gradient of the training point, which is corrected by the local curvature described by the Hessian. So this basically you can think of it as a similarity measure between 2 points, between the removed training point and the test point, corrected by how they are looked at by a model. So this influence function will be large for similar gradients, for similar vectors, and it will be smaller for more different vectors, right? So this gives you really a notion of similarity in the model internal representation. Okay, so with this tool, you can do two things, as I mentioned. So first of all, this is what we touched upon doing this geometric interpretation. We have the similarity analysis. We can see what data are similar to each other. And with that concept, we can understand what machine learns. But also we can look at which data characteristics are influential. If removal of points with certain characteristics makes a large difference for the model, it means that this characteristics was influential. Okay, that was probably a little bit complex, but we got there. So to sum up, I discussed autoencoding. I discussed clustering. K-means clustering which was I guess pretty simple. It's a simple clustering algorithm. Then I discussed autoencoders, whose job is to reproduce the input data at the output. And in the meantime, you have a bottleneck which forces the algorithm to compress the information about the data. I showed you how you can reproduce the phase diagram of autoencoder via anomaly detection scheme. And I discussed influence functions, which are able to extract a similarity concept from the machine.
Anna,
so there are
can I have one question?
Please,
This
yes.
first method, this correlation method, this was not machine learning. They were just you just meant the classical clustering methods, right? I mean,
Yes. Yes. However, you're definitely right. But some people are saying that clustering can be thought of as one of the simple machine learning methods in a sense of this, this definition, right? So the more data, the better our clusters, right? So
right. But this is just a statistical method.
yes.
I mean, and this is very widely used in all data analysis in many different fields of science. I mean, so that is rather well developed also. I mean,
Yes.
right? Yeah. Okay. So I just wanted to make sure. Thank you.
Yes, exactly. Yeah. But that's exactly what we wanted to do. In a sense, we wanted to start with the simplest possible methods, and only if they fail to do something more complicated, because otherwise, it would be just doing something sophisticated for the sake of doing it. So it doesn't make sense. Okay. So our first approach was to really to do the. So I skipped that, but okay, I will tell you it like this. So we first tried to do clustering for raw data, but we didn't see anything. Okay, what I'm saying, we weren't happy with the quality of the clusters when we did it on raw data. So just raw time of flight images like that. So we thought, let's make the task easier for the model. Let's for the clustering, what I'm saying, and let's train the autoencoder, and then we will do the clustering, but on this latent space representation of the data, because it should be hopefully easier then. So what we did, as I explained to you, we input many examples of this time of flight image, and we were saying to the model, find such parameters find such connections between your neurons that you output exactly the same picture. And on the way, there was this bottleneck which we're gonna analyze. And if we do just this, we put all information, put time of flight images from whole phase diagram, and we do the bottleneck analysis, and then we do the clustering. No, well, it's terrible. We don't see anything here. And even what is even worse, so we plotted the data according to the known churn number. As I told you, this is proof of concept, so we were cheating sometimes and trying to understand what's going on, why it's failing. And there is no sensible clustering of data due to the churn number. So what we are trying to do to understand it better, instead of feeding whole phase diagram, now we're analyzing the cuts for phase diagram for separate autoencoders to try to understand what's confusing the machine. This was our question, because now we know this is not that approach, but why it's not working. And when you train your autoencoder in this way and analyze the latent space like this, we start seeing something. So there is some circular tendency of the data. You can feed the ellipse here. You can there are some different radiuses of this and this ellipse, and there is some angle here. There is some structure to the data. And interestingly, but it was of course us trying to understand what's going on. If you compare this angle to the micromotion phase that you have in the data, you see a perfect relationship, kind of indicating very straightforwardly that autoencoder learns micromotion phase, and this was the dominant feature it found which was needed to learn to reproduce the data. And it kind of makes sense, because if it's kind of rotation angle, you need to know it to reproduce well the data. However, it looks like it won't be helpful for analysis of for detecting topological phases. However, we still didn't give up. We were trying to extract from as much possible information as possible, and we're trying to see, because there is some clustering according to the radius. And if you plot the radius as like separately for every cut through the phase diagram, there is some separation. So this should be two trivial phases, and this should be topological phase. So there is some separation of phases, but not so well. So we thought that the next step which is needed to extract something better from this data is to remove the micromotion phase. And by the removal, I mean fixing. So all data has the same micromotion phase. Of course, perfectly, what we could do is to ask experimentalists, please just give us this kind of data and get rid of all others. But they weren't super happy to do the experiment all over again, just because we didn't want the micromotion phase to be there. So we turned to machine learning approach to fix the phase. And how did we do that? So this is this autoencoder with question neuron that I was mentioning before. And now I hope you will see exactly why it's useful. So again, the task is to reproduce, to compare some kind of image. In the beginning, without the question neuron, we wanted to reproduce exactly the same image at the output. But this time, we pair time of flight images which have all the same experimental parameters apart from micromotion. And as a question neuron, we give the difference of the micromotion phase between two images. And the task for the autoencoder with this question neuron is to, given this input image, reproduce the image that looks almost like this, given the difference between the micromotion. So we basically wanted to create a machinery that would be able to rotate, or to fix, to change the micromotion phase of any image by any phase that we want. And thanks to training on many pairs of such data, we were able to finish with to came up with the autoencoder, which we can then use in such a way. We input various time of flight images. As a question neuron value, we put just the negative value of this phase, and it will fix the phase to 0 for any time of flight image. So that now we are finally getting rid of this quality. We even confirmed that we got rid of it with influence functions. So this is the data across one cut of the phase diagram again. And the idea was to check whether after fixing the micromotion phase, maybe we still have some leftovers of this quality. Maybe it's just, we see by our own eyes that something changed, but maybe we left some numerical leftovers. Yeah, we left leftovers. And how we approach that. So in the first picture, you have how influential are data, how similar are data to each other before fixing the micromotion phase. And this is as a function of micromotion phase. And there are 5 diamonds of 5 blue diamonds, 5 red diamonds, but they are on top of each other, so it's not visible. But all the most similar, the most influential points are focused around the same micromotion phase, showing it's the most influential feature across this cut. And after fixing the micromotion phase, these are the same data but processed by the autoencoder and now they're supposed to have the same macromotion phase. You see that they are much they are influential. It's much more distributed across the macromotion phase, indicating that it stopped being such an influential characteristic. So now we have post-processed data. Now we have the in time of flight images with fixed macromotion phase. Let's do again what we did before. So let's do the autoencoder, this time with question neuron. And again, the task is to reproduce the input image at the output. And let's again cluster the latent representation of these images. And now it's better. So we see some, maybe it's not still not clustering, but we still it's more smeared out. This is all data. But now if we plot separate single cuts through the phase diagram, it clusters better. And if you do the clustering, the simple clustering, cut by cut, we can get such a phase diagram. And well, it's not very beautiful. As you see, we wanted to see these two topological phases and these two trivial phases, and we see something in between. And even there are this ugly, first of all, there are these ugly anomalies, and we don't see any we don't have any distinguishing between topological phases, which is the main problem. So instead of that, because now we were just doing the clustering in the latent space, now we turn to the anomaly detection scheme I was telling you about. So we train in a part of your phase diagram, and then we try to reproduce all other time of flight images, and how much your autoencoder is wrong indicates different phases. And this is much more clean. We don't have this anomalies that we had from clustering before, but we still don't have any discrimination between topological phases. And I mean,
sorry, one question. But those three different regions, there are different phases, those three that are distinguished here?
So what we were wanting to here, we wanted still to do this unsupervised learning. In a sense, we are pretending to not know that these two phases are different. So what we are feeding what we learned from clustering, kind of. So we are telling to the algorithm, this is one phase because this is what we got from clustering. Right. This is second phase, right, and you can train on that. And this is the third phase.
But in reality, those were three different phases or not?
Topologically speaking, no, because topologically speaking, this and this should be the same phase. But it would be impossible for any machine learning algorithm to tell us, no, okay, it would be possible, sorry. Yeah, but this is distinguished as two different phases, even though it's the same. I mean, it's not the same. But both are not trivial topologically. But as you can see from the time of flight images, this is high frequency regime. So it's when you really shake your data pretty hardly. And this time of flight images are super different from these ones, even though it's the same phase topologically, right? So it would be very tricky for the machine to tell you that it's the same phase. I don't, yeah. So this is one of the limitations of such approaches, especially when it comes to topological models. Okay, so from this approach, we got better borders, better boundaries between phases, but it's still not perfect. And most importantly, we don't have any discrimination between topological phases. So we got this phase, these borders. And the final thing that proved to be crucial is our influence function. So what we did, we trained a model in supervised way, telling him, here are points from phase 1, here are points from phase 2, here are points from phase 3. And here what happens. And then you analyze this model with influence functions. So these influence functions are telling you which data points processed by a model are viewed by them as similar. And and you always need to calculate influence function between one test point and one training point. So this is these are influence function values of all training data across the phase diagram for this single test point. And this is how the values are looks like across this dashed line. And you see that this phase is pretty uniform. So the values of the influence functions are pretty similar across the phase. Here is similar. The values are similar across the phase. However, here is something else that I may discuss later. Because it's everywhere, the influence is mostly 0, because the model was very sure that all these high frequency phases points are well classified. And finally, when we look at the uniformity of the second phase, influence functions are telling us two things. First of all, it sees two plateaus of similarity, and this difference is 1 order of magnitude difference, so it's pretty large difference. But even more importantly, we have drops of influence function values, so drops of similarity measure in between these phases. So it kind of indicates some additional boundaries that we missed in our first labeling of the phases. And we claim that we can discriminate between topological phases. However, this is what Professor Diepenbach also mentioned. We still, here, model still thinks that this phase and this phase, this high frequency and low frequency phase, are different phases, which is not true topologically. So it's still not, it's definitely not perfect, but nevertheless, it's first time to the best of our knowledge when we had any sensible results in a fully unsupervised way from experimental data describing topological model. So to sum up, we applied autoencoders and influence functions to the Floquet realization of a two-dimensional topological Haldane model. The micromotion phase turned to be the dominant feature. We derived all machine learning predictions, so we had to fix it. And we used another machine learning approach, so autoencoder with question neuron to do that. And finally, we recovered a full topological phase diagram without any a priori knowledge. And this is with the question mark, because in the end, we didn't have nice qualities of clusters, which was, that was enough of motivation to try more complex algorithms. But in the true scenario where we didn't expect additional phases, we may have stopped at some simpler and some simpler earlier stage and just say, oh, we did it. And now we were adamant to finish because we knew that we are missing something. So I would be kind of careful to say that it was without any a priori knowledge. And it was in a fully unsupervised way. At some point we used supervised approaches, but we fed it with labels discovered with unsupervised approaches. So that's it. Thanks a lot for your attention. And of course, code is always available. And if you're interested, please ask questions or go to the publications here. So thanks a lot for your attention.
Thank you very much.